All right, good evening, folks. So today we're looking at writing linear quadratic systems. Um, and what that means essentially is we're going to write two different, a linear and a quadratic equation. Okay. So just kind of refresh what we've already talked about. And first of all, it's also just, I'm doing this a different way today, just to kind of try it out, see how it works out in terms of um, doing this. But there are three possibilities when it comes to solving a linear quadratic system. And essentially the first one you want to know is, when you have a no solution, meaning that your linear line does not actually cross your quadratic in any form or fashion. Okay. You could have a one possible solution where your point of intersection is the tangent point, where it only crosses the line at one spot, kind of like, here. And then you have your secant possibility. And I said, I hadn't talked about secants yet, but basically where the linear line crosses the quadratic in two different spots. So here and here would be your two solution points or points of intersection for the system. Okay. So we're still looking for the same thing. The difference is now that in order to do this, we're going to have to learn how to write the pieces. Now, we've seen this formula before where we have V naught and have H naught again. And again, that just means V naught. That stands for initial velocity. Okay. And your H naught stands for in the initial height. Okay. And then the second thing is we have a linear where you're going to have Vt plus H, where V is your constant velocity. And the reason why it's constant is because we're talking about a linear line. Okay. And then your H is going to stand for your starting height. Now, before I get into this, just so that you know, yes, initial height, starting height mean the same thing. I'm differentiating them because sometimes the words initial will be used versus the word starting height. Same thing with initial velocity versus a constant velocity. So know that your constant and starting height are going to be matched up with your linear equation, and your initial height and initial velocity is going to be matched up with your quadratic equation. Okay. So when we do these, we're going to be filling out basically this part here, and on the linear, we're going to be filling out the V and the H. Okay. So that's what we're going to be looking at. The next thing also knows I'm doing this algebraically using the quadratic formula again. So there it is. Okay. And the last thing that's kind of sort of not new, but we haven't talked about this in a while, is the reasonableness of a solution. What happens is that you might end up with two possibilities, but based on the situation, you only need one or a certain one of them, or the other one doesn't make sense for certain reasons. So when we talk about reasonableness, that's essentially what we are talking about. So that's kind of what we're looking at today. Okay. All right. Actually, let me see if I can write it this way. Nah, it doesn't do any good. I'll keep it this way. I was trying to find there's a better way of doing this, but no, this will work. This will have to. Let me see. That might work a little bit better for me. All right. So when we write inequality, wrong subject, wrong concept. In the equation for the quadratic and the linear, and again, I went ahead and put these up here. You can kind of see which equation I'm going to use for which one. But when I go through here, I look for keywords. Like right here, it talks about an airplane that has a constant rate of 25 feet per second. Okay. At the same time, you have a ball that's launched from the ground with an initial velocity of 90 feet per second. Okay. So you want to write the two systems of equations. Okay. So what you look for is you say, well, on this right here, we know for sure that you're going to end up with a negative 16t squared plus your initial velocity, which was in this case 90 feet per second. So I write this as plus 90 feet or 90t, sorry. And then the initial height. Well, it doesn't actually tell you what the initial height is here. Oh, well, no, it does right here. From the ground. And we know that the ground is 0. So that being said, we don't have to worry about initial height here because it's 0. So that's what our equation is going to look like. On the linear equation, and again, I look for the VT right here. And I know that my linear equation talks about the model airplane with a constant rate of 25 feet. Well, the v is the constant rate. So I'm looking at 25 t. And again, it doesn't give you the initial height or the starting height in case of the plane. So we assume that it's going to start at the ground again, which would be 0. So I'm not going to write the 0 for the h, but it would be 0 here, and it would be a 0 here. So we're not going to actually write those. So now I want to actually solve this. And so like we did the other day, where I set it up, the two equations equal to each other, 25t, okay? And then you kind of rewrite some things a little bit. So it's minus 25t minus 25t. Oops, just kidding. So that your equation looks something like this. T squared plus, so 90 minus 25. And again, if you're not sure, put it in your calculator, like I do here, which is 65t. And we know that's going to all be basically equal to 0. So now I can actually solve this. And there's a couple ways you can solve this. I'm going to stick to doing quadratic formula just because that's what we've been working with. And what's nice is that this is A, and this is B, and I actually don't have a C in this case. So C would actually be 0 in this case. So I set it up, negative B plus or minus the square root of B squared minus 4 times A, which is negative 16, times C all over 2 times A. And then I do my discriminant value, which happens to be this number again, in the calculator. So 65 squared minus 4 times negative 16 times 0, which again, if you know anything, this whole second part is going to be 0 anyway. So essentially it's 65 squared. So then I end up with a negative 65. Just kidding. Negative 65 plus or minus the square root of 4225, which in this case is going to actually be 65 again. So it actually works out nicely. Divided by negative 32. I know I'm going to get two different answers on this. Okay. So if I do this, I do a negative 65 plus the square root of 4225 all over, darn it, hold on. Sorry, I forgot to do something. Negative 65 plus the square root of 4225 all over negative 32, kind of like this. And I get the first answer to be 0. That's nice. I do the same thing for the minus part of this. And I get the second answer to be, I need a decimal. 4.0625. So roughly 4.0625. Okay. And then what I want to know is, when does the plane actually hit the ball? So here's kind of the thing, and this is where the reasonableness comes into play. If I use my equation here of 25t, if I do 25t times 0, then I know that this second answer here is going to be 0, 0. So that's not the one I'm looking for. What I want to know is this right here, because this is 4.0625 seconds. So if I take my linear equation again of 25 and I multiply that by the time that I know, then what it tells me is the height at which the ball or which the plane, hits the ball itself. Okay. So when I do this is basically what I find out is that at and I'm running out of space here, 4.0625 seconds, they collide at 101 feet, points 5625 in the air. And that would be my intersection point that I am looking for. Okay. And I apologize, it looks kind of messy, and I know that. Again, I'm trying this a little differently this time. Issues with my printer, in case you're wondering. But that's essentially what you would do for this. Okay. Again, I get the 0.00, but again, because that doesn't not the point I want, that's not the reasonable point. That's the point I'm looking for. So at 4.0625 seconds, the ball and the plane itself are at 101.5625 feet. Okay. That's the intersection point. That's the collision point that occurs. Okay. Hold on, let me do something real fast. Okay, so then look at the next one. And again, try it first. I'll be back here in a second to show you how I did it. Okay. I will give you one right here. There's a 4-foot platform, which is going to change your starting height or initial height, depending on what you're looking at. Okay. All right, folks. So this is what I did. Here's what I got. Hopefully you tried it. So again, there's my first equation. Initial velocity of 16, initial height. Now, how did I know that the 4 went to 17? Because you have a helicopter. Sorry, you don't see that. Let me move this down. Because you have a helicopter here that takes off from a 4-foot with an initial velocity. And the fact that it says initial velocity means that I'm using that for my initial velocity here, which means that that 4, therefore, has to be my initial height. Okay. The plane's the same, so the plane doesn't actually change. It's the same thing. Okay. So I set it up equal to each other. I move my 25t over again to get -8. That becomes my A, my B, my C. So negative B, 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 A, C, A. I worked that out and I get two different answers. I get a negative 0.81 and I get a 0.31. I choose the 0.31 to get 7.7. Now, the reason why I didn't use this negative 0.81 right here has to do with, again, with reasonableness and the fact that because I'm talking about times and taking off, this negative 0.81 seconds would not count in this particular case. So the 0.31 is the one I use to figure out the height in which they collide. So at 0.31 seconds, they both collide at roughly 7.7 feet. And again, roughly because it's a kind of a decimal number. It looks like this, 7.725. So we're going to approximate to 7.7 feet. Okay. Which is kind of interesting because if we assume that the helicopter takes off, if we assume that the helicopter, the ball, and the plane actually take off at the same time, then this first collision actually never occurs because the plane and the helicopter will collide way before they even, throws the ball. So that's kind of just an interesting aspect of this whole situation, just, knowing those kinds. Okay. So example 3, again, it's more reasonableness. It's a little different because what I'm doing this time is we're giving you the quadratic here already done. We want to figure out the linear part of this. And normally I would do this backwards where I do this first and the other one second, but it's, I like to work backwards sometimes on these. But we do know a balloon is released in a 22-foot abandoned building at a height of 2 feet at a constant rate of 7 feet per second. Okay. So the linear equation for this, and again, I'm not going to write it like I did on the other ones, but basically I do know that the equation, is going to seem to be y equals 7x plus 2. And again, I know that because right here it says constant rate of 7 feet per second, which is going to be my velocity here, or my rate, really is what it is. And 2 feet is the height it starts at. Now, some people ask, well, what about the 22 feet? It's just extra information for the time being to get it. Now it says for me to find the 2 points of intersection. So again, it just basically means to solve it. So I'm going to do the work. And I realize I probably should have done this a little differently, but that's okay. I'm going to do the work right here because why not? And here I have x. I'm going to change this to x real fast. Kind of like this. Okay. Then I'm going to kind of set it up like I did a minute ago, where I'm going to solve everything. I'm going to move my 7x this way. Kind of like that. I'm going to move my 2 this way. Now notice there isn't anything to write with the 2. So what you need to know is the fact that you're subtracting it from 0 to look something like this. Okay. And then 50 minus 7 is 43. That becomes my A, my B, and my C. And again, I'm going to run through the whole process one more time just to kind of show you. So negative 43 plus or minus the square root of 43 squared minus 4 times negative 16 times negative 2 all over 2 times negative 16. And again, I'm going to get 2 answers out of this. So I'll do the number first to kind of see. 43 squared minus 4 times negative 16 times negative 2. That gives me 17. 1721. And I got to learn to write this a little better next time. But anyway, I'm going to get 2 answers out of this. So the first one, it looks like it's going to be negative 43 plus the square root of 1721 all over a negative 32, kind of like this. And I get, what did I get? I get up 0. The first one is 0.047. And then do the same thing for the other one. Make this a minus. And I get 2.6. 2.64. So now I want to figure out the y value to this, because these are just the x's. And so I go back and I pick this equation, because that's the easiest one to use. And so the first one I do, and I'm not going to write this out so you can kind of see it, but 7 times 0.047 plus 2, kind of like that. And the first answer I get looks like it's 2.3. Okay. And then I do the other one, 7 times 2.64 plus 2. And I get 20.48 as my answer, which begs the question, that I typed this in, right? But anyway, so I get 2 answers. I get 0.047 and 2.329. I'm going to check my math here in a second, because the answer to this should actually be higher than 20.48, unless I typed it in wrong, which, wouldn't surprise me if I typed it wrong. Not typed it wrong, wrote it wrong. So I'm going to check this graphically real fast to make sure that I just didn't type it wrong, which again, nope. Oh, that's fine. I'll be right back, folks. Oh, I'm back. Anyway, so here are the 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 – 2 You have this one and this one. And the question is, which of this point is not reasonable and why? And what was supposed to happen, and I think I didn't type this wrong, right, like I was supposed to. These are both correct points, but the idea was supposed to be this, so that you know. And I'll go and change this later on. But basically, this right here, I'm going to change this to 18 just to make it make sense to what I'm about to tell you. Okay. And I will make that change. So here's basically what happens. This first answer makes sense because at 0.047 seconds, they will the balloon will be popped at 2.329 feet. Okay. This one is not supposed to make sense because if they collide at 2.64 seconds and they're in a space of 20.48 feet high, what it's supposed to be essentially is the fact that the building is only 18 feet high, which is why I think it was just a typo on my part, meaning that this point is not even possible because the building itself doesn't actually fit within this particular point. And so this point's not supposed to be reasonable. Well, now the other thing you can also argue with this, that even if this was a 22-foot building, this answer would also not make sense because of the simple reason is this. If the balloon pops here, therefore, this point never actually occurs by that logic. Okay. So either way you look at it, this first point is the only one that actually makes sense in terms of the situation itself. So that would be the only point I would need. I'm gonna change this to where this it's supposed to be this, which is supposed to be less than 20.48. But that's basically what the answer is supposed to be. That this one doesn't make sense because the building is only 18 feet tall, and this is showing you a height of 20.48 feet. So I apologize for that. Anyway, so that's when we talk about reasonableness. Last one, and I question myself now when I type these out, what I'm actually typing. But try it first, and then I'll come back and show you the rest of it. All right, this is what I got. Okay, and again, I got 2 points. I got one at 0, 0. I got one at 1.56 and 140. So first question, and again, how long does it take the opponent to pass it up? It takes about 1.56 hours. And I guess maybe we're on the Autobahn or something. I don't know. At 140 miles is when they catch up. The 0.00 is not reasonable because, in this case, because this is the point where they actually pass each other, where Weston passes the opponent's car up. Okay. So the answer we're looking for in this case to answer the question is actually this right here. Okay. There you have it. Again, quadratic formula is you're going to be your best friend on these. So, make sure you learn it. All right. We'll see you all around.